All right, cool. Let's start our second task for week 6 of remote learning. In this case, we are using that information that we used in that last lesson on Lewis structures and having it determine the shape of molecules. So the success criteria for today is that you should be able to determine the shape of simple molecules. And the way we're going to be figuring this out is by looking at the Lewis structure and understanding how many pairs of electrons I have and how that's going to repel to result in our shape. So we need to think in the 3 dimensions of the shapes. You might be asked to draw them, and some things I just want to point out when it comes to what 3 dimensions are referring to. Whenever you see straight lines, that means that it's within the plane. Whenever you see a dashed line, it means it's behind the plane. And then whenever you see a bolded line, it's coming out at you from the plane. So it's just kind of sticking at you. And you see how that one is behind. It's how we can communicate 3D structure in a 2D writing. And you may be asked to draw these sort of things. The main thing to remember is that you should always have 2 things that are within the same plane, and then the other 2 show the other 2 planes. So do kind of keep that in mind. So you could also draw 2 bolded lines, 1 straight line, and 1 dashed line, and that would be correct in orientation. But I normally just draw it this way to keep it simple. Cool. So when it comes to the shapes of molecules, you have to remember that these electrons are negative, and so like charges are going to repel. So these clouds of electrons are going to try to move, so that way they have the maximum distance apart with the minimum amount of repulsion. And that's then going to take the shape of that molecule and giving that 3D shape that we now know. We refer to this as the valence shell electron pair repulsion, also known as VSEPR, as the justification for it. So 2 things will factor into the shape of molecule. The first one is going to be the number of regions of electron density around the central atom. We always refer to the central atom when we're talking about shapes. The other thing that's going to affect the shape is how many of these electrons are in bonds and how many atoms are around that central atom. So let's look at some examples. The first step is basically what you have been doing in that previous lesson, which is figuring out the Lewis structure. So I had 3 examples that I wanted to do, and I'll fold the paper again. Some of them actually we did as examples in the last lesson. So I'll just quickly draw the Lewis structures of them. If you're not confident with Lewis structures, I suggest you go back. So we are going to do CH4, CO2, carbon dioxide, and we're also going to do ammonia, so that way you can see a fair number of examples. So those are my 3 molecules that we're looking at today. I'm just going to quickly draw the Lewis structures. Now, if you're not confident with the Lewis structures, do go back to that lesson. And like I said, you kind of semi-memorize them as you go. All right, so those are my 3 examples that I'm working with. When it comes to Lewis structures, the first thing I want to do is count the number of regions of electrons around that central atom. This is going to determine bond angle when I look at this. So when I say central atom, I'm talking about that guy there, and that guy there. Cool. They might give you some larger molecules, and you'll see this in the CPR quiz, and they'll tell you then what you should be referencing to when you're doing that larger molecules. So if I was to count the regions of electron density around that central atom, I have 1, 2, 3, 4. So in this case, I have 4 regions. In my second example of carbon dioxide, I only have 2 regions. So that double bond actually counts only as 1 region, not as 2 separate regions. So that's 2 regions. And in this case, I have 1, 2, 3, and that lone pair is my fourth one. So this one also has 4 regions. So why do we do this? Well, the reason why we are counting regions of electron density is because those regions of electron density are going to try to repel, so that way they're the maximum distance apart to minimize that repulsion. So that goes back to what I was saying with the shapes of the molecules and that Vesper theory. That will then determine the bond angle for those molecules. So with 4 regions of electron density, those 4 clouds are going to separate so that the bond angle is 109, and it should technically say 109.5 because that's the geometry number when you actually divide it by 4. In this case, if I have 3 regions, I divide it by 3, and so my bond angle is going to be 120. And if I only have 2 regions of electron density, my bond angle is 180. So that's the first thing that we need to know when it comes to our shapes, is what sort of bond angles we are working with. So, let me just double check so I have the right colors. All right, so in this case, because I have 4 regions of electron density, that bond angle is 109.5. This bond angle, since I only have 2 regions, is 180. And then this bond angle, because I have 4 regions, is going to be 109.5. If you wrote 109, they would still accept it. Cool. So that's my first step. The next step in determining shape then is to figure out how many are bonded and how many are unbonded. And the reason why that matters is because, as I said in the previous slide over here, shape is also affected by the number of bonded atoms. The thing to remember about the non-bonding electrons is that they aren't drawn in the final shape, but they affect the shape. So let's see what I have here. So in this first example with methane, I have 4 regions of electron density. All 4 of them are in bonds. In this second example, carbon dioxide, I have 2 regions of electron density. I should say both. Use good English. Both are in bonds. And then the last one with ammonia, I see that I have 1, 2, 3 are bonded. And I have 1 lone pair unbonded. So like I said, what that means is that that lone pair will affect the shape but not be drawn in the final shape. So now let's look at our table of possible shapes. So this first table that we're looking at, we are thinking about the ammonia example and the methane example. So they both have the same bond angle because they have 4 regions of electron density. But using this table, you notice that there would be 2 different shapes. So the methane, the CH4, is going to have a tetrahedral shape, whereas the ammonia, because it has a lone pair of electrons, is going to have the triagonal pyramid shape. So we see here the drawings of the Lewis structures, and then we see down here the 3D shapes. And what we notice is that the atoms are 109.5 degrees apart from each other, but in this case you can see that there is an empty space up here with the nitrogen, and that's because of those lone pairs of electrons there. So it affects the shape, but it's not drawn in the final shape. I could also have a bent shape. So in this case, I still have 4 regions of electron density, but I only have 2 unbonded, 2 that are unbonded, so it creates that kind of bend shape with a 109.5 degree angle. So let's write down those shapes. So this one here is tetrahedral. Sometimes they ask you to draw the shape, so do be mindful that you know how to draw it in the 3 dimensions. We'll skip carbon dioxide for now. We're going to go to methane, or not methane, ammonia. And we can see here how I've left that top bit blank. Oh, and I should write down the shape. That is a triagonal pyramid. Cool. So those are those two shapes. You do have to have these shapes memorized because they're not going to give you a table of shapes. All right, cool. These two examples here, we are looking at if I had 3 regions of electron density and 2 regions of electron density. So be mindful that the ammonia that I just drew is not an example of 3 regions of electron density. It's 4 because of those lone pair of electrons. But if I had something with boron, for example, which is happy and stable with 6 electrons, then it could have 3 regions of electron density. The other option is I have something that has a single and a double bond. Cool. Bond angle is 120, and then once again we look to see how many are bonded and unbonded, and then that determines the shape. In this case, with the carbon dioxide, there was 2 regions of electron density. There's only one shape possible for that, and that is linear. So again, if I was to go and draw this, I would state that guy is linear, and that's all I would draw. So remember that when you're doing the 3D shapes, you are not drawing any electrons anymore. Cool. All right. So some things to keep in mind when you're answering NCA questions then regarding shapes. I would let me backtrack. With the NCA question, they're going to most likely give you 2 molecules, and you're going to be comparing and contrasting these 2 molecules. My suggestion when it comes to scaffolding your answer is start by talking about 1 molecule, write it all the way through, and then explain the second molecule. So with that first molecule, start with saying the number of electron density regions, talk about VSEPR, and then use that to justify what the bond angle is. Once you have bond angle justified, you can then start justifying shape, and with that, you state unbonded and bonded electrons. With that, it's really important that you do this in that order. I find a lot of people rush their answer and they jump straight into shape, and they totally forget to justify bond angle, and that will normally limit their answer to a merit or even an achieve, depending on that marking schedule. Then, after you have finished explaining that first molecule, start on that second molecule. And when you start on that second molecule, use a linking comparison word, because there's usually something similar about those 2 molecules that you can then use to explain, even though they have this as a similarity, they are different shapes or different bond angles because, and then explain the why. And that why is just the same thing with the process. Talk about the number of electron density regions, VSEPR, bonded and unbonded. So let me show you 2 examples of how, what kind of combinations they could give. So for example, if we just look at the ones that I did, they could give you both methane and ammonia as your comparison, and they could say, how come they have the same bond angle but different shapes? Or when you're writing up and justifying it, you would say they have the same bond angle but they have different shapes because, all 4 of the bonds, or all 4 regions are bonded in the methane, whereas only 3 of them are in the ammonia. So that's what you're going to be using. Another common one they like to use is the bent shape. So they'll give you 2 bent shape molecules. One will have an angle of 120. The other one will have an angle of 109.5. And they'll ask, why do they have the same shape but different bond angles? So those are common things that they like to pair together. The other thing they might try to pair together is number of bonded atoms. So for example, you could have 3 bonded atoms to the central atom in both of those cases, but why does one result in a triagonal pyramid and the other one results in a triagonal planar? So they will pair things to allow you to do that comparison. And that comparison linking word's really key. I have seen it in the marking schedule that for the excellence, they were looking to see a comparison word. So make sure you have it. Usually what I see for the merit is that you get a merit point for each one of the molecules you've justified, and then the excellence point is that you've justified both, and usually there might be a little asterisk that you have used a comparison word as part of that justification. So watch out for that. All right, cool. So to recap, you should be able to use the Lewis structures to determine shapes. And with that shape, you should be able to justify it based off of the electron pairs, how many atoms are bonded, and the repulsion theory. So go ahead and move on to the Mahi choice. Like I said, it's all listed on my Google site. You're not expected to do all of it. It's just to give you some choices, and all the resources are on the Google Classroom. The last task for this week is going to be a CPR quiz. So make sure you have a good practice on Lewis structures and shape before you attempt that CPR quiz.